This talk is the Terzaghi lecture I gave in 2019 in Philadelphia, roughly a little over 4.5 years ago. I've only made a few changes and added or subtracted some slides, otherwise it's identical to what I gave at that time. I don't think it's gone out of date because it is a perspective over the last 60 years. So I'm not trying to get... It was up to date at the time I did it. If I were doing it today, if I were redoing the analyses, I might do a couple of things a little differently, but not much really. Anyway, this is what it is, and I will start by, and then regarding the site response. And of course, whenever you give the Terzaghi lecture, you have to show a photo of Terzaghi. He passed away in 1963. I was just started my last segment of my graduate study in 1962, so I never had an opportunity to see him, meet him, or shake his hand. So, but be that as it may, here he is. He was, and we'll proceed on that basis. The talk I'm giving this afternoon consists of 6 parts. Since it is a retrospective on site response, and why do we need site response? And to do a good site response, you need an input motion. So what input motion we need to do, and what has nature told us about that? And then I'm going to talk a little bit about the comparison of empirical earthquake ground motions to see whether what we've done so far with all these recordings, does that make sense? Just a very brief sort of a high altitude overflight on that. Then some historical perspective, just what happened from 1950s all the way to the present, more or less. And then some, what are the currently available analytical procedures, and how well do they do? And I have a couple of examples to show that. And finally, of course, you always have to have some concluding remarks and some recommendations. So part 1, why site response? And I just have a few nice photographs. This is the new East Bay, San Francisco-Oakland Bay Bridge. Some of you may recall that that bridge suffered damage in Loma Prieta earthquake in 1989, and the state of California started working on replacing the east segment, which is about 3 miles or roughly 5 kilometers, in 1991. And finally, this new bridge, which is a cable stay bridge, it's a beautiful bridge. The segment of it is cable stay, was dedicated in 2013. So that's how long it took to, because first they wanted to remediate it, and they found out that there's no such thing as a reliable solution. So they decided to replace it, and that took all that time. And initially they thought the cost was going to be $1 billion, US dollars. It ended up being $6.5 billion. And you do need site response to evaluate all the things that go on in this. Another very important facility is a nuclear plant. This is the Diablo Canyon nuclear plant in California. I worked on the Bay Bridge from that 1991 until dedication, and then a few more years after that. So it takes a long time to get these things done. And I worked on Diablo Canyon from 1989 until about 2015 or thereabouts. So that's another site that required a lot of site analyses and evaluations. And of course, everywhere you go in the seismic zone, you have to worry about buildings. And I've worked on a couple of these, not that many, because I stopped working on buildings after I left private practice. And of course, since this is the mining group, so to speak, we have to show a figure of a TSF. This happened to be Cerro Corona, which I worked on from 2006 until 2019. So was heavily involved in that as well. This is the this is the tailing dam, and it's a downstream construction. And this is of course, the pond with all the tailings in. And the beach is forming very nicely so that they can build the Christmas tree. But those are just to show you some nice photographs. Now let's get into the nitty-gritty. Now typically we'll have a soil profile like this. I'm sure there's no such thing as a uniform soil profile, so there'll be variations. And if there's absolutely nothing on top of it, we call that free field. So a point A and a point A and a point A along that top of that profile will be the free field points. And to do an analysis, we need an input at the bottom of that soil profile, because typically we look at a soil profile sitting on top of a rock half space, and we need that input. And except for some Japanese data, we actually have very little at that depth and at that location. So we really have very little things to rely on unless we use strictly mathematical simulations. And I think mathematical simulations are only good if we can calibrate them with actually what nature has done. And since we don't have many recordings at those depths, and we know that what's recorded at D is not only influenced by what's beneath it, it's also influenced by what's above it. So, but we do have a lot of recordings if there was no soil, but only a rock half space, like a situation like this. We have lots. We used to have only, when I first started in 1964, we had about 7 or 8 recordings. Now you'll see how many we have when I go through what's available to us. So this one we can get a handle on, but we need to really find this number, and so that we can put it through a soil profile. And if we have a structure, whether it's a building, a dam, a nuclear plant, or even a tunnel going through, eventually we need to know what B is, and then we need the various points within the structure itself. We certainly have we have practically none for B. We have a lot of A's, depending on the site conditions. We don't have any D's to speak of, but we do have the C. But we have ways to translate, knowing C, we have ways to translate that to D, and then putting it through the profile can get at A, B, or anything. But for A, we can do a one-dimensional analysis. For B, or if we happen to have a dam instead of a building, or where the idealization may look something like this, then we'll need to do something more complicated than a one-dimensional solution. And that's some of the things we've been talking about the last 3 days here. Programs like two-dimensional FLAC, or three-dimensional FLAC, or Plaxis, and so on and so forth. So we will find the input C based on what we've been observing over the last so many years. Then we can, given what we have over that profile, we can convert it to D and put it into the system using whatever program we choose to use. But then we're going to calculate things along the surface and within that profile. So we know that we will be calculating numbers at what we call the free field at either end of a system like this. So that's where, again, we go back to recorded motions to say, can we now, what we're calculating, can we compare that to what nature has shown us, and therefore calibrate our model? So that's the nature of the beast, so to speak. And that's why we need to continue to keep the site response up to date and as best as we can, and we always need to keep an eye on what nature keeps telling us. A lot of times it tells us something we thought we knew, but then find out it's really something different. So we have to be on our toes, so to speak. So the ground response analysis provides a means to check the results in the free field of dynamic analyses that incorporate soil structure interaction or soil foundations structure interaction. Therefore, it's important to have in our computation toolbox or bucket, depending on which way you like to call them, procedures and computer programs that we can rely on to provide us with the reasonably reliable estimate that correlate well with measured values and are physically meaningful. Before I get into what procedures those might be and how they evolved over the years, let's take a quick tour of what nature has shown us about recorded earthquake ground motion. And one of the parameters that has come into play over the last, maybe starting about 25 or so years ago, is a parameter called VS30. How many of you have heard of that or used that? Well, that's good. And to be sure that we're all on the same plane, so to speak, let's see what the definition of VS30 is. VS30 is a time average shear wave velocity in the upper 30 meters of a soil profile. Or a profile, it doesn't have to be soil, it could be rock as well. Thus, if the upper 30 meter consists of n layers, n sublayers, each having a shear wave velocity VSI, I being 1 all the way to n, then VS30 will be 30 divided by the summation of the thickness of that layer divided by shear wave velocity. In other words, how long does it take for the wave to travel from one sublayer to the other? You sum them up, that's the total time it'll take from bottom to top. You take 30 and divide into that, and you get the VS30. Or schematically, it looks something like this. All these equations. Now, anybody who wants a copy of this presentation, I'll be happy to send it to you. I sent it to Kathy, and she's going to send it to all the participants that suffered through 3 days since Tuesday morning over here. But if anybody else would like to have a copy, of course, you won't have my email address, but I can go back to the first page, and or you can ask Kathy for my email address, and she will give it to you, so you can either ask me a question or ask me to send you a copy of this or any other reference I refer to today. Now, what has happened in the last almost 20 years now, it's exactly 20 years beginning next year, a group of people got together all over actually, but it was centralized at the University of California at Berkeley in what's known as the PEER Center, Pacific Earthquake Engineering Research Center. And the project was called the New Generation Attenuation Relationships, NGA, was initiated. At that time, it started out by looking only at what was recorded in places like California, Japan, which we call shallow crustal earthquakes in active zones. Then it expanded, the first collection was from 2004 until 2008. We were able to collect only this much data. Before that, we had this much, collected this much data. Plus, there was a uniform processing, uniform assignment of values, whether it's the magnitude of the event, the distance, or site conditions, and so on and so forth. Because prior to that, any researcher then went on their own, so to speak, and they would have a VS30, let's say, that were, or a shear wave profile that was different from somebody else because they had no access to all the data at the same time. That was the nice thing about this NGA project, is that offered that opportunity to homogenize the data and so make it uniform plus acceptable to everyone. It was all verified, checked, peer-reviewed, and so on, very thoroughly. That project, that first project, which we called West 1, NGA West 1, because it was mostly based on California data and a lot of Japanese data, but in a few other locations, was expanded in 2010. The other one was finished in 2008. Became NGA West 2, again for shallow crustal events in active zones, and that would include California and Japan. And by then we had the earthquakes in New Zealand that added tremendously to the database, and a few other places. So more than doubled the number of data points, recorded motions. And that was completed in 2014. Since then, 2 other projects have been started, actually 3, but the third one is just beginning. But 2 others that we started and completed, the NGA East, which would be in something areas comparable to Central and North and East North America, meaning that Eastern Canada and Eastern United States. And that would really for the stable continental tectonic regions. That probably could apply to certain places within Australia, not to New Zealand. They're part of the active. And then, of course, the subduction, the NGA subduction, which was started about 4 or 5 years ago, was just completed last year. And, all the papers have been published, all the reports have been published, some of the papers have still being reviewed. So that's the process. And for the NGA West 2, the number of recordings is about 21,000 more or less, and about 19,000 of which were usable on our what we call that free field, the point A I was showing earlier. And the range of data was from magnitude 3 to about almost 8, and the distance from very close to 1,500 kilometers. When you get to these long distances, engineers' interest sort of wanes significantly, but seismologists like to look at some of those data. They're very useful. And for the site conditions, they vary from about 90 to about 2,000 meters per second. For the these are the range of data. I'm going to go on that. This is just the magnitude and distance up to, plotted only the numbers up to about 500. And you can see how extensive. What's really important is that how many now we're getting very close to the source. Still very sparse, but significantly more than we had before that. Especially what we had when I first started in this arena, so to speak. The NGA East, they collected about 9,000 points, of which about just shy of 9,000 were usable. But unfortunately, or fortunately for whoever lives there, the earthquakes have not been that large. There was slightly less than 6. And that's a lot of those data came from Canada and from parts of the eastern part of the United States and some other stable regions, some in China, I think, and so on and so forth. And this is the variation of what the site conditions and distances were. But because of such limitations on the data, in terms of, they actually relied more heavily on simulations. So they tried to correlate with the smaller events and then extrapolate the large events. And this is what they look like in terms of plotting. For the subduction, they got 70,000, of which about 49 were usable. And this is a range similar to the others. Now for the subduction, you have to worry about 2 portions. One is the shallow one, which is called interplate, and one is the deep one, which is called interslab. So everywhere you have a subduction zone, whether it is in Chile, in Peru, in northwest United States, like Northern California, and in Washington or Western Canada, you always have to worry about either one. So the data were collected accordingly, and the treatment of the modeling that was done accordingly. And that's what they look like. Now, what can we learn from that, and how do we apply it to what we need to do a response analysis? And I went through this and examined that, and without boring you in any details, but I'm just going to go to the details that what we have done, what we've recorded is usable, and the models that have been developed are usable, provide reasonable results for rock outcrop motions for that point C. For other sites, I cannot say the same thing. I know the modelers have, worked their heart out, so to speak, but they're not as well done because they're assuming certain simplifications on nonlinearity of soils that really the physics do not support it as well as they should. And you can't make the model so complicated that it becomes almost useless. So we have to be sure we are a lot more careful. For the rock sites, there is hardly any nonlinearity to worry about, and as a result, it's much simpler to build a model that's not extremely complicated, although many of them are now extremely complicated, but not extremely complicated to the point of almost being useless. That still, if it provides results that correlate well with the actual recording. So we're in good shape as far as that point C. When we make the comparison at point A, we're not as good a shape, especially the softer the material is. A lot of times, what we are doing for major projects like a water dam or a TSF is really not worrying so much about what the accelerations are or what the spectra are, which we would for a building. We're more worried about how much displacement there is. And that part, as we've been discussing the last 3 days here, has been correlated with other observations, cases where we have actual deformations observed in the field or from recent physical modeling, so we have a better way to get the correlation with, as long as we have a good handle on what the input should be. So having that point C reasonably well defined is a very useful thing to have. So now what do we do with all that? This is the one we already talked about. So let's now just take a little trip down memory lane, so to speak. This goes back to actually 1906, and there was a big earthquake in San Francisco. And San Francisco has the huge variety of site conditions. And even then, the geologists and the seismologists, there was no such thing as soil mechanics or geotechnical engineers. Terzaghi wasn't active yet. And so the performance at various sites during 1906, not performance in terms of what the motions look like, but in terms of what damage occurred or what pattern of deformations, like sliding into the bay and so on and so forth, happened. That the performance of various sites during the 1906 San Francisco earthquake highlighted the importance of site response during that earthquake. And Lawson, who wrote a report about that earthquake after it happened, emphasized the effects of local site conditions. There were some attempts to do wave propagation work, but it was not very successful. Certainly they had no way to make any calculations besides adding a few or multiplying a few numbers. So there were no computers then, for sure. But so it wasn't really until the 50s when Professor Kanai in Japan started saying, well, I really see these effects and we really need to start looking into them. So he proposed the use of the continuous solution of the wave equations to study the side effects on earthquake ground motions. Computer was just coming into play. It was not that easy to do it. The formulation of the continuous solution requires that you have a constant viscosity, which translates into a variable damping in the whatever system you're analyzing, and that is not the way soils behave, and that really didn't get off the ground very much. Plus, it was extremely cumbersome to calculate because you need to, first you need to get the Fourier spectrum, some of you know what that is, and then convert back, and the processes to do that were extremely cumbersome. So they didn't go very far. But the Professor Martin Duke, who at the time was teaching at UCLA, visited Japan and came back with what Kanai had been doing, because the people in the United States were not that aware of all the work that Kanai had done. And he brought it back in about 1958. That's the year I finished my bachelor's degree, so it was a long time ago. But that was really met with a strong resistance, especially from the structural engineers, saying, no, there's no such thing as side effects, so stay away from us, so to speak. And then as we progressed into the 60s, the late Professor Seed, Harry Seed, who was my advisor and my colleague and friend for some 25 years, from 1964 until 1989 when he passed away. He wrote a paper for the World Conference, which was in 1960. I think that was in New Zealand, or somewhere around that part of the world. And advancing the concerns with behavior of soils during earthquakes and the potential effects on of local site conditions and earthquake ground motions. Now, as you know, I'm sure all of you have heard of Professor Seed, but the 60s was quite a productive decade. That's when Ken Lee, under his and the Professor Seed's direction, started the cyclic triaxial test, which shed a lot of light on how sands behave during under cyclic loading, and which led to the liquefaction evaluations that we talked about quite a bit the last few days. And I happened to come along, and we started these analyses, and others came along, and so on and so forth. So that was a good jumping point, so to speak. But also, in addition to that, there was Professor Hudson at Caltech, who made some tests on some buildings in Hawaii, and found out that as he increased the level of shaking the building, he saw that the steradic loops he was measuring were beginning fatter and fatter, and therefore there was more energy dissipation. So he proposed that when the analysis be done, that they should vary the damping with the level of shaking. He did not do anything about the slope. And then two other professors at UC Berkeley, Professor Benzine, Joe Benzine is a structural engineer, and Professor Seed, formerly with the student at the time, they were given a contract by the state of California, because the state of California was worried about building bridges over soft soils, driving piles, and what will happen there. And they developed a very advanced program, actually called a bilinear program. So instead of following the loop like this, they just basically replaced the loop, the steradic loop, by two straight lines, but they created a loop. So how large or how small the loop is dictates how much energy is dissipated. That was done, finished in 1963. I'm glad it did, because without it, I probably wouldn't have been able to do very much after that. So, and then Professor Martin from UCLA again suggested the need to incorporate the influence side, but that didn't go very far then at that time, because in 1965 and until 1971, when the San Fernando earthquake occurred, and there was a huge failure, a slow failure of the San Fernando Dam, the people who worked on earth dams at that time just said, earth dams are always safe during earthquakes. Because what happened, well, two things actually happened. One we knew all about, which is what happened in 1906. About 4 or 5 clay-type dams were subjected to the shaking during the 1906 earthquake, and hardly any of them suffered any damage. So people got sort of lazy, so to speak, or lax. There was a failure in 1925, but that was a 8-meter high dam, so it's like a little dike, so who cares? So nobody was paying attention. But I think it's really important to keep in mind that a lot of things sometimes happen in this world, we don't hear about them much later. So in 1939-40, there was a big earthquake, somewhere I think 1939, there was a big earthquake in Japan that nobody talked about because at that time everybody was busy with the bombs and the war. And resulted in the failure of quite a few dams. And, but it was never reported internationally. It was some reports written in Japanese. Nobody was reading those reports. And we didn't become aware of them until late 70s, actually. So had we been aware of that, we may not have had some of the problems like San Fernando Dam. But be that as it may, we eventually caught up and we started paying a lot more attention to dams. And what I did as part of my thesis was I examined the laboratory test, and that's when I suggested that we really should not do just what Hudson had done, which is allow for the damping to increase with the level of shaking, but also change the modulus. And that was the start of what we call the equivalent linear solution, which I recommended that in my thesis, but I said I ain't gonna wait until I do it. To submit my thesis until I finish that. That can be done afterwards. Because to me, the purpose of a thesis is to get the degree. not to make a name for yourself. Just get the degree, then do something very useful. So keep that in mind if you're still a student. And then so Professor Seed and I finally developed using the bilinear solution to confirm that we can do it. Because you need a way, how are you going to do this analysis? And what do you correlate it to? We had no measurements to correlate it to, so the only thing we had was a method of analysis to correlate one another. And so what we did was what Penzian, Parmalee, and Seed had done was to take this loop, which is typically what you measure in the laboratory, or if you're shaking a building and you have the correct measurements, you'd get a loop looking like that. They change it to a bilinear loop, which is two straight lines, and it just keeps on oscillating. If the level of shaking is large, it gets bigger, and if the level of shaking is smaller, it gets smaller. And what we did was to take that loop and replace it by a slope, and call that the equivalent modulus, depending on how large the strain is. If the strain is very small, it's going to be a larger modulus. Slope will be like this. If the strain is larger, it'll become a lower modulus. So the modulus is the slope of that line. And the area of the loop is the amount of energy dissipated or the damping. So that's what we replaced that with. And when we ran an analysis using the bilinear solution, we got, this is some typical loops that we got from the analyses. When that part of the shaking was very small, we got a very small loop. When it got bigger, we got a bigger loop. And then we went back to, in parallel, we're running an equivalent linear analysis where we replaced these by that slope and that area to represent the equivalent modulus and the equivalent damping. And the result looked something like this. This is the bilinear solution. This is the equivalent linear solution. Bilinear solution, equivalent linear solution. And I don't know if we didn't put them next to each other. Maybe we were afraid they may look too different. But when you look at them this way, they don't look that far apart. And I think I'm going to go. I don't have the results digitally, so I can't plot the points directly. Otherwise, I would have done it for this. But I think I might go back and digitize them and see how close they come. So I think, because I'm trying to finish writing the paper so it'll be published, so not just presented. Continuing on what was going on in the 60s, while we were doing all this work on the analytical side and some of the testing side, but only for strength, not for properties, Professor Richard at the University of Michigan was really undertaking a major program of measuring modulus and damping values using beginning in 1960, and he had quite a few students at that time. Harding, who developed a lot of that work, Olson, Ken Stokey later on in the 70s, and so on and so forth. So that actually began to create a database that we can use to see how things will vary, and that's really was the basis for what Professor Izzat and I did, because Professor Richard was very generous, gave us all the data. A lot of it they had published. But one thing they were doing was reporting everything in terms of amplitude, not in terms of strength. But we found out that really you need to look at strength, so we just took their data, and it's very easy to just take how much it moved to, what was the initial height for a triaxial and so on, and get the strain. And that's when we came up with that report that has been used quite thoroughly since 1970. And the idea of a G over G max, which is really now part of the lingo in geotechnical earthquake engineering, was created as part of that effort. And this is what that G over G max looks like. This is G over G max versus strain. And typically when nowadays you get, oops, gotta get that. So and typically you see quite a variation of these. This may be for the stiffer the material and the deeper it is, the flatter that these curves, G over G max is a function of strain. One of the things that I've seen happen quite often is a lot of people will get some samples taken in a laboratory and they'll measure a maximum modulus, because they can go down to some strain levels. Not everyone is capable of going down to as small as 10 to the minus 4, but they can get close to that, and therefore call that the maximum. And then they continue the test, and then they say this is what we'll use in the field. That could be extremely inaccurate, because a lot of times when you actually have both measurements, the shear wave measurements in the field and the sample you took to the lab and measured the maximum, what you think is the maximum, or the lab-based maximum shear modulus, which translates into a velocity, it's somewhere between half to maybe 2/3 of what you would get out of the field. So then the idea, and this is really based on what Professor Ken Stokey, University of Texas, who's basically the premier fellow in terms of understanding soil modulus and damping and how they vary with strain for all kinds of material. I'm sure all of you, anyone that does any dynamic analysis in soils has to know his name. So. And what he suggested is that you take the shape of the curve from the laboratory, because we don't have that shape in the field, and assign it to a maximum shear modulus that comes out of the field. So you take the shape of the blue line, and then you move it up to meet the field maximum modulus, and that becomes the G over G. If you divide it by this maximum value, it becomes the G over G max. And that's how he constructed his relationship that everybody uses now. Somebody in Stokey or Stokey and somebody, so they're all over the place. He's a fantastic fellow. And so continuing on what was going on, Professor Kovacs was running some shaking table tests on some slopes, and we said, well, why don't since I had developed some programs to analyze not only one-dimensional, but also two dimensions using finite elements, why don't we try to see if we can capture what he did, the results of his shaking table test. And we found that we were really missing what's happening at the crest of the slope and at the toe of the slope. And then the idea came up, but well, maybe what we were doing is overestimating the damping, because at that time we were using one single damping value throughout the finite element mesh. This is how crude things were. I'm talking now about 1968, 69. That's a long time ago. So then I went back to the drawing board, so to speak, and reworked the problem to allow for varying not only the modulus, but also the damping from element to element. And when we did that, it really improved the comparison with the actual And there's a paper on that in open literature, so you can see that if you want to. And that led to the sort of creation of this program we call Quad 4, which is still in use. And, but it's an equivalent linear, not a non-linear program. Then Schnabel came around 1971, and Professor Seep was his advisor, so he asked me, I was still working part-time at the university, he asked me to sort of get him going, so to speak, and we started to see how can we improve, because what we do with the Quad 4, what we were forced to do was to use Rayleigh damping, because we could not do that with the other modal superposition, which what we started with, where you can have damping that's independent of frequency. By using Rayleigh damping, then you are actually forcing the damping to be a function of frequency. And you know, if you've ever done work in vibrations, that goes by a factor of 1, 3, 5, 7. So it rapidly goes, and the damping becomes really large at the very high frequencies. So we wanted to see if we can, how can we improve on that? We're going back to basic principles, and we encountered the same problem that Kanai had faced, which is if you use the equations of motions based on the wave propagation, the continuous wave propagation, you start out by assigning a viscosity, and that leads to a constant viscosity that leads to. But fortunately, Professor Leismer, who had just joined the university, he finished his PhD at Michigan with Professor Richard, but he came to Berkeley to teach. But he was working for a long time on the foundation vibration problems. He was worried about how can we isolate a machine so it doesn't, the vibration doesn't affect the next one adjacent to it, and so on and so forth. So I was talking to him, I said, we have this problem, we just cannot, how do you have any ideas how to suggest it? And his answer was unbelievable. He said, well, we don't know what the viscosity should be, we don't know what the damping should be. We measure damping in the laboratory when we take the area of the loop, but really don't know anything beyond that. So why do we assume that the viscosity in these equations is constant? Why don't we just change it and say, let's change the equations to put a constant damping so the viscosity becomes a variable. And viscosity does not affect the results of the response. And basically that's how the program Shake, which I'm sure many of you have used, hopefully, or are familiar with at least, was born. Plus, at that time, and Schnabel was a very bright fellow, actually, extremely bright, he found a program which was just recently developed by Cooley and Tuckey that allowed the fast Fourier transform. So that the problem that Kanai faced was really cumbersome to go from Fourier to the time domain was much simpler using this tool. And that's what made it possible to create a program like Shake that became it still is actually, extremely popular and useful. And Leismer, of course, suddenly started working more and more into the arena of earthquake engineering rather than foundation vibrations. So then that gets us to topic number 5, which is how well do we do with the available procedures that we have developed over these years. This is extremely helpful to use. Making sure you get it next to your mouth so you Theo will probably get tired from my complaining. Hi, Theo. Okay. Well, we have these procedures that I talked about, which is the equivalent linear program like Shake, which has really been used quite a bit. People have used finite element programs that were created for two-dimensional virus running in one-dimensional line. But that's equivalent to using something like Shake as well. But since then, of course, the nonlinear programs have become into play and more usable and more user-friendly, and people are getting familiar with them and are using them. And among these is the program called Deep Soil, which was created by Professor Hashash and his colleagues at the University of Illinois, which can be run as an equivalent linear or as a nonlinear program. So we had and then of course you have FLAC, which can also be run actually as a quasi-equivalent linear, because it doesn't have the iterative abilities, but you can assign some properties that you make it close to that. But it's really most useful to run just as a nonlinear program. So I took the Treasure Island site, where we have a recording at Treasure Island and one nearby at a rock outcrop, a very close distance away. And we know that when we do a Sheik type analysis, equivalent linear analysis, we get very good comparison between what was recorded and what we're calculating. So I examined that using all these three programs. With Sheik, it's equivalent linear, so I can compare it to the equivalent linear of Deep Soil. With Deep Soil, it's nonlinear. I can compare it with the FLAC, the nonlinear. So we have a comparison: equivalent linear, nonlinear, and of course, equivalent linear from both to nonlinear from the other two. So the good comparison to see how well we do. Treasure Island is not large shaking. It's about 16% of the ground surface. At Buena Island, it was about 5 or 6% shaking. So it's not a very large shaking. So the nonlinearity was not very strong. But at least it gives us a feeling how well we can do up to a certain point. So here we are. This is Treasure Island. And this is San Francisco, and that's Berkeley and East Bay, and the Bay Bridge is right over here, and Treasure Island is over there. Actually, I bring that's Treasure Island, and nearby Buena Island is just south of that. And if you have a close-up, this is Treasure Island. That's the Bay Bridge. Go through a tunnel, first through a part of the bridge actually goes over the island, and then the tunnel will get you into the west side, which is a suspension bridge. And so this is the site of Treasure Island, and this is the site of Buena, which is a rock site. And so we were able to use this input into this. And just to let everybody know that this is where Berkeley is, and this is where San Francisco is. So. And if you prefer to see it through Google Earth, this is what they are: the Bay Bridge, and then the Treasure Island and Buena Island. The site of Treasure Island was, since the Loma Prieta earthquake, was investigated quite a bit. Before that, we had not extremely good information about what's at the island. But since then, it had been investigated quite thoroughly, and basically it looks like this. You have some sand over the young bay mud, which is a soft clay, and then somewhat denser sand, and then the old clay, and so on and so forth. And you get into the Franciscan rock, which is not a very hard rock, but still shear velocity around 1,800 meters per second. That's pretty good shear velocity. So when you look at the shear velocity measured by various people by various techniques, they're pretty tight, and based on that, established a best estimate for the shear velocity. The purple line, which looks something like this, and then now you can discretize each of these layers and run whatever program you want to run. And the recordings were like this. If you look at the spectra, the Buena Island is the blue line, the Treasure Island is the dark black line. So you can see that whatever motion was on rock was amplified. Now this is the sea in that sketch I said about before, But we have a way to convert it to a D before we run the analysis, because D is the one that should drive the profile. And it becomes a slightly modified C. And that modification depends both on what the velocity of that material is sitting on, and also what the properties of the column above it. That's why you can never take C and use it as D. Some people unfortunately do that occasionally, but we should not do that. And when you put the blue line into that profile and you shake, you get the red line, and which is pretty close but not exact. And if it were exact, actually I would worry. And if it were really different, I would really worry. So, but it's pretty close. And if you vary the properties a little bit one way or the other, you're not changing the final outcome that much. So all of these little lighter black lines are the variations of properties, and the red line is what our best estimate of the properties was. And now one thing that we talked about that to the group that was here the last 3 days, what if we did not have Yerba Buena Island, but for the Loma Prieta and the Bay Area, there were 9 other recordings on rock outcrops. 2 in the East Bay, 1 in Berkeley, 1 in Piedmont, and 5 in San Francisco, 6 in San Francisco. So what if we did not have Yerba Buena? Would we be stuck using one of those guys, or maybe there was only one, like it used to be in the past, but Loma Prieta was rich in data, which was very fortunate. So we went through that and ran the analysis using Shake, using the other 8 recordings. And this is what we get when you use Yerba Buena, which we know is reasonably good. But when you use the other 8, you get the cloud of the yellow, of the green line, the green was. None of which comes close to correlating with the actual recording. So you really always have to be, and it also emphasizes how important that input is. So when you worrying about a dam or something, be very careful how you select the ground motions. It's extremely important. But fortunately, in this case, we did have the neighboring, and we'll continue using that with the other programs. So now we're going to compare the equivalent linear and the non-linear, and using shake and deep soil. This is, again, the black is the recorded at Treasure Island, the blue is the Yerba Buena. We put that into the deep soil, but using the equivalent linear approach, and we get the green line. It's a little better here than shake, and a little worse here than shake, but overall it's comparable to what shake gave. In fact, this is what they look like, practically identical. So they're both either reasonably good or reasonably bad, so depending on your viewpoint. And then if you do use deep soil nonlinear, this is what you get. Again, it's very good at this location, slightly worse here and here, but then equivalent linear, but still a reasonable replication. It's a little bit deficient here because it's probably over-softened the system and therefore lost some of these higher intermediate frequencies. This is the high frequency range, this is the low frequency range, and this is the intermediate, so it's maybe lost some of that, whereas the equivalent linear didn't do as bad a job there. You can see that, how much higher it is. But for both deep soil and shakes, it's not a matter of which program. And then we went to FLAC, and this is the layers again. When the FLAC, you have to assign a stress-strain relationship for each sublayer, and we have quite a few of them. For the sand, the upper layer, which is the sand fill, the water table is, I think, this is a meter, about 3 or 4 meters below the ground surface, so anything above the water table is assigned a more Coulomb. Below that, it was assigned a PM4 sand. The clay, initially we tried the hysteretic model, but with the modulus and damping coming from Vucetic and Dobry for what the PI is for that young behemoth was about 50. Then we did it with the PM4 silt, and so on and so forth. It's all written here. And those of you that do use FLAC are completely understand what I just said. Those that don't will just have to take our word for it, so to speak. Is that all right? And this is what the results look like using FLAC now using the hysteretic model for the clay, not the PM4 silt. It captures the essence of the result, the essence of the recording, but higher numbers. It did not lose those intermediate frequencies. Which, to me, that was very encouraging, actually. I felt very good about seeing that. When you use PM4 silt for the clay, it got even better. It's almost, it's actually the best comparison, except it gives us a little higher acceleration. So if we look at the spectral shapes, which is, the spectral shape is just looking at the each spectral value divided by the peak acceleration. So you always get 1 at this very high frequency, 100 hertz here, 0.01 second for the period. And so you're getting that 1. And if you look at the spectral shape using FLAC, whether either one, whether you use the hysteretic for the young behemoth or the PM4 silt, you get almost identical. Not quite, but almost identical. And then if you look at deep soil, the shape is not as bad as it looked before, because now we're dividing by a lower acceleration, so these numbers came up a little higher. And then you look at all of them, they basically cover a good range. The least, the worst in this is actually shake. So, but still within reason. And it's the same. So now we just plotted the actual recording and see how close they all come. They all do very well at this peak. The nonlinear solutions do better than the equilinear solutions here. They all do about the same over here. So that's the way it is. So now this is the part that developed in terms of looking at spectral values, and I think it's very encouraging to see that you can get reasonable answers as long as the input is not that high using equilinear. The nonlinear does really well with Treasure Island, whether it's deep soil or FLAC. That's very encouraging because we are relying on FLAC heavily to make a lot of decisions for tailings dams, for water dams, for tunnels, all over the world. This is a very useful conclusion to find out. Now, one of the things we also worry about is how much pore pressure might develop. And since we have we're doing these runs, and FLAC automatically calculates the amount of pore pressure that is generated, and so we can see what it looks like. So again, looking back, and now we use only PM4 silt for the clay and only PM4 sand for the fill. The rest were the same as before. And if we look at the pore pressure in the sand, just a couple meters below the water table, it actually was very small, and you can see it's practically zero until you get the really high peak of the. This is the acceleration at that depth. This is what that area was feeling during the earthquake, because the input was the 0.9 and modified from C to D at the bottom, and we're just running it through, and at that depth of about 7 meters, where we roughly measuring the pore pressure as well, this is what the accelerations looked like. And when the acceleration got to a fairly high level, the maximum, the pore pressures got up to about 4%, very low. But when you look at the young behemoth, as the shaking just got to the first peak, it started really rising up to about 20%. Now the level of shaking is not very large, and we didn't get to anywhere near 40, 50, 60% as we normally worry about, especially if we're looking at a tailings dam or a water dam. So that at least it's very useful to look at that. Plus, what this tells us is we got to be a little careful with equivalent linear solutions if we are worried about how the motions are going to transmit from a certain, well, let's go back to the profile here. If we start here with the D input, because we estimated the weight on C when as if there was no soil, then we change that to a D and then push it through the profile, and this motion is going to propagate upward. If there's pore pressure here, that means they're going to soften the site. You got to soften this layer, which means they're going to transmit lower and lower frequency, or prevent the transmission of the higher frequency. So act almost like a isolator. And any structure on top of that, whether it's an embankment or a building, would be affected by that. It may lead to higher deformations because now it's softer and could move more, but in terms of inertial forces, they would be reduced. And in some cases, it's more important, the effect of inertial forces is more important than displacement, sometimes the other way around, so you have to be careful. And having the ability to accommodate what that effect might be is a very useful thing to have. And that's where flat comes into play. We haven't tried it with deep soil, so I can't say how well that will work. Nobody, as far as I know, has tried it with Laxus, so we don't know how that works. I know no one has tried it with all the other programs that typically people use for nonlinear analysis. And I think someone needs to start thinking about those issues a little bit more. Okay, so there's we're getting to that beautiful end, the concluding remarks. And it's very comforting that something you started 60 years ago still appears useful up to a point. And it's widely used, that's for sure, because it's so easy to do. And for getting site response and for developing site-specific earthquake ground motions and design parameters. It has also been widely used for evaluating existing and new earth structures and for assessing SSI aspects. Now, the thing to keep in mind in here is you deal with, I don't know if all of you, but certainly the majority of the ones I've been talking to for the last three days deal with mining projects. And these typically are the tailings dams. And they tend to be on the softer side where nonlinearity is an important issue. But if we build really a good dam, a water dam, except maybe for the core, the shell should never get really into a nonlinear zone. It should be strong, it should be very dense, and it's easy to do that. Therefore, using an equivalent linear analysis for that should be a perfectly good, legitimate process. And in fact, what I recommend if you're involved in a project that involves such a dam is to actually make that run to see what kind of numbers we get. And then if the regulator or if the owner or the engineer is really concerned and wants to see what happens if I did a nonlinear analysis, at least I know that they should not get much beyond that point we got with the equivalent linear. So it becomes sort of like a good back of the envelope check on the more detailed analysis. Because after all, we should always keep in mind that when we do an analysis, we do it to get some insight. Not to say this is the God-given number, let's use it. So that's very comforting to see. Next, we say advances in nonlinear analyses are encouraging, and the results presented today highlight the values of using such analyses. And since then, this is 4 years ago, since then I think things have, our understanding has improved. Some of the details have, we discussed earlier today in formulating constitutive models is improving. So basically we should stay tuned, so to speak. And what's important really for practicing engineers is to try their best to stay in touch with what the literature is producing. And there are about 5 or 6 individuals all over the world who are leading all these efforts, and it's always good to stay in touch with them. Care must be exercised in selecting appropriate constitutive models for the various soil layers. And calibration of the selected constitutive model with relevant test data and empirical correlations are essential, as we talked earlier today. I know that Professor Hashash, who developed the deep soil, and his collaborators have done that for the model built into deep soil. And Professor Boulanger and Ziotopoulos, who've done the PM4 sand and PM4 silt, are doing something similar. So keep an eye on what they publish. The results for the Treasure Island site using PM4 silt for the young bay mud highlights the importance of accounting for pore water pressure generation and cyclic softening during shaking. And the key factors that affect the site response calculations are the input motion, as we saw with all those like cloud of green values compared to the red one that we got when we had what seems to be the best input for the other site, or the more appropriate input for the site. So the input motion can have profound influence on calculated site response, as evidenced from the results shown earlier for the Treasure Island site. And the soil profile will also have influence, because when you saw some differences, but not as large as the ones with the input motion, the soil properties will influence the result. We saw that in some of the variations and how things vary when we used the hystereticol or the PM4 silt for the clay. There was some difference, but not a huge difference. The method of analysis will influence the results. We didn't see much for the particular site, but some other results that I've seen, either for a dam on a foundation or for a site, a one-column site, also show a little more difference, especially when the level of motion is higher. For the Treasure Island site, the effect was minimal for the level of shaking experienced in the Loma Prieta earthquake. And then some recommendations, and here's a plea. Please limit the use of the golden linear procedure to those in which the calculated strain is less than 0.6%, or the maximum strain is less than 1%. I see this abused so much, it actually, sometimes I wish I'd never developed a golden linear solution. Some people go to 3–4%, that's nonsense. That's utter nonsense. It was never intended for that, so please don't do that. Unless I don't think you're interested in deconvolution. Hardly anybody uses that anyway. Now comes a very important point about you gotta take into account uncertainty. And again, I see so often people doing a blind or a black box simulation, Monte Carlo realizations, and allowing the properties to be absolutely nonsensical. You know, you take a nice, reasonably dense sand and you assign it a shear velocity of like 80 meters per second at a depth of like 10 or 20 meters. That's nonsense. And you get results saying, oh my gosh, if this could be so and so, then you better do something. That's nonsense. You got to be careful what you assume. And so a law of variation in shear wave velocity and in modulus reduction, and then within physically meaningful ranges. When using a randomizing process, like the one I just mentioned, a law of variations in these properties, be sure to check that any realization is physically meaningful. And I'm not the first one to say that. I'm just emphasizing what others have said it for years. Because Grande, when he gave his Terzaghi lecture, he was number 2, I was number 55. Emphasized the need to select a probable range of pertinent soil properties, guided by judgment and experience. This is very valuable to keep in mind. And finally, I want to give you some parting thoughts. I don't know what they mean, but they sound interesting. Confucius said life is very simple, but we keep insisting on making it more complicated. You know, it's simple to put it like this. This is complicated. My arm hurts. Now, my arm is ruined by legs now. Then Einstein said, everything should be made as simple as possible, but no simpler. Thank you very much for your attention.